Okay, in this presentation we are going to look at the normal approximation of the binomial distribution. Now, I'm going to be very quick with this question. Really, the key hazard with this question is really that it doesn't really make it clear what you're needed to do. So it's just actually sort of thinking through it a bit. And that's really the point of this particular video, just sort of spotting what to do. So a fair die is tossed 180 times. Okay, so that's a large number of trials or a large sample size there. Okay, determine the probability that the face 6, face 6 will appear between 29 times and 39 times, and then less than 22 times. So really the thing here is actually just sort of noting it that it is a binomial distribution. Okay, with n equals 180 and p is equal to 1/6, where a success is a 6. Now I'm just going to put that in there as a face 6. The 6 in a circle means the face 6. Just actually make a statement there, really, when you're doing these sort of things, just to actually formally state what a success is. Okay, now I'm not really doing it there properly, but just make sure you do it. Okay, so between 29 and 39 times inclusive, and then less than 22 times. So really, this is very similar to the other videos that I've done previously. Now, so just as a sort of quick remark, what we're going to do here is use our continuity correction factors, which we will use when we approximate a discrete probability distribution like the binomial and the Poisson with a uniform the normal distribution. Okay, sorry, actually I did state it there. I'm making a liar of myself. Just remember to put in sort of a couple of statements like that, okay, at the start of your answer sheet. Okay, now the couple of key things here: mean and variance. These are things that you should know. Definitions, they're probably going to be in the back of your exam paper. N times P times 1 minus P. Sometimes I write that as Q. Q is the probability of a failure. Essentially, what I'm saying here is that you should really be able to quickly work out the mean and variance there, okay, of the binomial variable x. Okay, so essentially what we're going to do is something I should actually do here also is I should justify it, a large sample, and just make a statement that the central limit theorem validates this. Well, if it doesn't validate it, it sort of lets us assume that we can do this using the normal approximation with a continuity correction with x approximated by this approximation here. Okay, so we're going to approximate our binomial variable x with this normal variable x, a sort of an approximation which is distributed with a mean of 30 and a variance of 25, 5 squared. Okay, now, so this is the first question here that we're asked. Okay, this actually I should have just sort of done that, make a little mention of this. This is when I apply my correction factors. Okay, so you notice that it goes from 29 to 28.5 and then 39 to 39.5. That's employing a couple of these here, like for example x less than or equal to n, that's for the 39, and x greater than or equal to n, which is 29. Okay, so that's how we get that. Okay, now I'm going to skip over this. Usually what I would do is make more of a big deal about the calculating the normal probabilities. Now hopefully you should be fairly familiar with that, but when you calculate it out, the z-score should be between the z-score in both cases should be, or in the first case should be minus 0.3, and in the second case 1.9, and then you should be able to work that out there and get a probability of 0.5892. So if you're not really familiar with this stuff, I suggest you go back to the normal distribution questions there. That's a fairly standard normal distribution question. That's what I'm looking at there. Okay. Likewise, down here, probability of x is less than 22. So that's the binomial, and when we adjust that to a normal approximation with the continuity correction factor, that becomes x less than or equal to 21.5. The z-score is minus 1.7, and that gives us probability value of 0.0446. So that's it. Yeah, we'll leave it there.